Good morning, Physics 20. I hope you guys are all having a good day so far. Today, ladies and gentlemen, we're going to be working on Newton's laws of universal gravitation. So, this is a really cool topic. This is a really useful topic. And ladies and gentlemen, the skills that you're going to be learning with these formulas, with this video and the next several videos up and coming, anytime we're dealing with gravity actually, is going to be really important for Physics 30. As here, we're looking in Physics 20, we're looking at gravitational forces and fields. And then next year in Physics 30, you guys are going to get to look at electric forces and fields and magnetic forces and fields. And the skills you learn here are going to be very valuable to the skills that you're going to be needing to be successful in your Physics 30 next year. So if you'll notice in your assignment, there's a lot of questions about gravitational stuff. And that's why I left so many of them in that assignment. Sounds good, guys? Ready to rock? All right. This is going to be a really long video, guys. So I will be, throughout the video, I'll be recommending pause locations. So then that way you can stop the video and go do some practice problems and then keep going, that kind of thing. All right. So buckle in, get ready for a long video. We're going to start with the awesome pun. The rotation of the Earth really makes my day. Get it? Yeah, it's pretty sweet. All right, so here we go. So we're going to start off with something that is already familiar, an equation we've already used. So you guys have already seen this equation when we've talked about weight in dynamics. So we already know that the force that gravity is applying to an object is called its weight. We already know it depends on the mass, so how much stuff an object is made out of, and the acceleration due to gravity. You guys have already seen this equation before. It is right there on your data sheet. Okay. Please excuse the wonky W's. I have no idea. The computer rebelled and took my really nice arrows and turned them into ugly W's. So there, we can fix that. All right. Now, ladies and gentlemen, on average on Earth, our acceleration due to gravity, or G, is 9.81 meters per second. Now, the key thing here that's going to be very important as we continue, this value only works near the surface. So let's write this down. Only works near the surface of Earth. Okay, the second that you start going off into orbit around Earth like your satellites, G is no longer 9.81. Okay, so we're going to talk about that a little bit later, and why that is the case, but this number only works near the surface. So G, ladies and gentlemen, isn't necessarily always going to be 9.81 now. Existential crisis starting. Sorry, guys. All right. So, ladies and gentlemen, we'll start out with a couple of questions using our G equals Fg over m, or Fg equals mg, in a couple of different ways here. All right? Okay. So, an object has a mass. So, we got a mass of 22 kilograms and a weight of 36 newtons. Now remember, ladies and gentlemen, that the second you see weight is the second it means Fg. Okay. And on the surface of the moon. Now remember, ladies and gentlemen, the moon is going to have a very different acceleration due to gravity than Earth does. So what is acceleration due to gravity? Near the surface of the moon. You're going to be seeing that phrase more now, either near the surface, or you're going to be seeing it Questions like in orbit, something like that. We're above the surface of the Earth. All right, well, our equation right out of the data sheet's already rearranged for us. Why do anything different? I'm going to plunk my numbers in, my 36 newtons over my mass of 22 kilograms. And ladies and gentlemen, plunk that in your calculator, 1.63 repeating. And now I need units and I need sig digs. Now, ladies and gentlemen, because it's 1.63 repeating, it means 6363363 dot, 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 dot. So when you're going to be doing your rounding for sig digs in units, no, you don't round for units, but you know what I mean. You are going to need to take that guy into consideration to round that one up. Okay, so our value is going to be 1.64 meters per second squared. Now, ladies and gentlemen, I said, what is the acceleration due to gravity? I didn't say magnitude. I want direction. Direction's down. Sounds good, guys? All right. Always remember, acceleration's a vector. Okay. Now, question number 2, ladies and gentlemen. An object has a weight of 84 newtons on Earth. Okay, so Fg, 84 newtons. What acceleration due to gravity on Mars will the same object have that has a weight of 62 newtons on Mars? Okay, well, we've got 2 sets of data here. I'm going to label them. This is the weight on Earth. We also know that G on Earth is 9.81 meters per second squared. That's a given. Now, once again, near the surface of Earth. Now, we're going to go back over to Mars here. I'm going to separate this into Mars. So my weight on Mars is 62 newtons. Now, notice how I've set up my data here. When you're dealing with 2 different planets, it's going to be a lot easier for you to organize your data in that way, to keep it in nice, discrete bundles, so then that way it's easier for you to access the data where you need it. So you have been asked to calculate what is the acceleration on Mars. So we've been asked to find G. Well, if we don't have G, we know our equation that we want is G equals Fg over m, but we don't have mass. Well, how can we find the mass? Guess? Come on, guys. Come on, guys. Shout it out. I'm talking to a computer. Shout it out anyway. We're going to calculate the mass on Earth first. Okay. We are going to calculate the mass on Earth first. Because remember, ladies and gentlemen, your mass doesn't change no matter where you are in the universe. It's because a mass is a measure of how many particles you're made out of, how much matter you have. And remember, ladies and gentlemen, atoms make us all matter. Yeah. Get it? Get it? Yeah. Okay. So, ladies and gentlemen, with this one here, we're going to calculate mass first, and then we're going to use the mass here on Mars, and we'll go from there. Okay. So, Fg equals mg. I'm going to use our rearranged version because why not? And this is on Earth. Now, I'm going to divide out my g, which will give me my m. So my mass of 84 newtons, divide that by 9.81 meters per second squared, and you're going to get the lovely value of our 8.5626 dot, 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 dot kilograms. Now that number is the same regardless of where you are. So that many kilograms is going to be the same on Mars. Okay, well, I'm going to go over here and do my math on Mars. So my Fg is now equal to mg. I need to find g. Whoops. Divide by mass, or just use the pre-rearranged equation on your data sheet. I don't really need to be doing this, but whatever. All right. Fg over m. Now I can use this mass over here. So my 62 newtons from Mars, I can divide that by my 8.5626 ... Use all numbers in your calculator. Do not round until the end. And G on Mars, 7.2407 ... All right. Let's get our answer written up with sig digs units and all that jazz. Now, 2 sig digs, so that means I want 2 sig digs. Well, that's not going to round up. So, ladies and gentlemen, we've got 7.2. It's acceleration, so meters per second squared. I said acceleration. I didn't say magnitude. So, yeah. Sounds good, guys? All right. So that's that equation, ladies and gentlemen. Now, we're going to look at a new equation. Now, the previous equation that we were looking at is when you're close to the surface of the Earth, where Fg is your weight, and Fg is still your weight when you're orbiting the planet. However, now we have a different scenario, ladies and gentlemen. We're going to launch ourselves out into space. Not literally, just mathematically here. I don't quite think a space trip is in the budget. So the force of gravity is always, ladies and gentlemen, going to pull objects towards the center of the planet's mass. Okay? The force of gravity is always going to do that. Always, 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 always. Now, notice how I very rarely say always. Okay? Now, gravity is what is called an attractive force. So it's going to pull things towards it all the time. Okay. Next year, and we're going to look at electric fields and magnetic fields. They can be either attractive or repulsive. So, I know, isn't that disgusting? Repulsive, repel, disgusting. Yeah. Couldn't help it. Okay. So that'll change next year. For now, we're always going to be dealing with only attractive forces. Okay, so the force of attraction that's going to be in between two masses, ladies and gentlemen, so say an object and a planet, or it could be, say, I don't know, my stylus for the writing tablet and my calculator. Okay, so these two objects are exerting a gravitational force on each other. I am exerting a gravitational force on the computer. And however, the thing is, ladies and gentlemen, our masses are so low that it's completely irrelevant. Okay? That's why objects aren't flying around the room towards you. Okay? Even if you have an attractive personality. Get it? Okay. So, ladies and gentlemen, this equation is called Newton's law of universal gravitation. And this is where you're going to find it on your data sheet. Okay, right there in the dynamics section. Okay. Now, M1 and M2 are the masses of the objects. So this could be a spaceship and a planet, if a spaceship's orbiting the planet or what have you. This could be my calculator and my stylus. All right. This could be any two objects. This could be me and my desk lamp, right? So R is the distance from the center, okay, of the object to the center of the second object. That is important, okay? So, ladies and gentlemen, less than subtle hint. And I would also say on test, because I do give a test question like this, but you guys don't get to see it because we're not doing tests. So this, ladies and gentlemen, is the center of Earth. And this red line here is the radius of Earth. Okay. However, we've got a spaceman, we'll say, I don't know, Mark Watney from the Martian. Great book, by the way. Awesome book. The movie was good, but it didn't capture the true spirit of the book fully, as movies never can. But books are always better. Read the book. It's amazing. And about the Martian, guys. I have my copy somewhere. I'm not sure where I put it. It's around here somewhere on my plethora of bookshelves. But The Martian, ladies and gentlemen, is an awesome book, and the physics is accurate, and so is the chemistry. So what Mark Watney did, or not Mark Watney's the character, Andy Weir is the author, he actually did all the math. He said in an interview I heard with him that he spent something like 3 days guaranteeing that the calculations that were necessary for Mark Watney to travel from this point to this point to get sure the exact distance was correct and that he was actually driving towards a particular crater. So the numbers that you're given have all been done and vetted by astrophysicists. So it's awesome. So definitely read it. It's great. Okay. So, ladies and gentlemen, there's Mark Watney floating above the surface of, well, it'd be technically Mars, I guess, if we're going to be accurate to the book. However, notice here, ladies and gentlemen, this is the radius that you would be using, okay? So if I say Mark Watney is floating this many meters above the surface of Mars, and above the surface of Mars, you need to take that radius of Mars and add it to how far he is above the surface. So I gave this value from the surface up to Mark Watney as x. R is the radius of Mars. So the R that you would be using would be the radius of Mars plus x, and that's going to be the R that you use right here in your equation. Okay, I will show you a calculation involving that. So be aware of that, okay? Okay. Fg is the attractive force between the two objects. It is in newtons, so it's our force of gravity. You could call it the weight if you wanted, okay? Now, ladies and gentlemen, I'm just going to scroll down here so you can see. There we go. Now, capital G is Newton's gravitational constant. Newton's gravitational constant is essentially what you could call 1 unit of gravity. Okay, 1 unit of gravity, 1 piece of gravity. This is how I like to think of it. Now, it's a wonky number, 6.67 times 10 to the power of negative 11. Do you have to memorize this number? No, you don't. Take your data sheet, go on to the back. On the back, you are going to find, in the same place where you find your value of 9.81 up here, go down 1, and you will see it right there. Okay, gravitational constant, big G, 6.67 times 10 to the power of negative 11 Newton meter squared divided by kilogram squared. Okay, now, why there's a G in there, I have no idea. Once again, computer rebelling. Okay. So, ladies and gentlemen, you don't need to memorize this number. One thing to keep in mind, though, ladies and gentlemen, is that big G is tiny, 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 tiny. It's a little number. 1 unit of gravity, as I like to think of it as, is minuscule. Minuscule. And what are the values that are going to be increasing the size of a gravitational force? Look at your equation. What do you think? What here is going to be making Fg larger? This is tiny. We're dividing by radius, and it's a square, dividing by a square too, so this number can get pretty big. It's the masses. The only thing that is going to make the gravitational forces actually mathematically significant is going to be the mass. That is why my calculator and my stylus, even if I put them really close, I can't detect the force of gravity between them. I mean, I could calculate it if I really wanted to, but the number is going to be so small, it's not going to have any practical value. So the only time that gravity and Fg is actually going to be significant is when at least one of the masses is huge, such as when we're going to be dealing with things like planets or suns, where the mass is just so big our brains can hardly comprehend objects that big. Okay, sounds good? All right. So, ladies and gentlemen, Newton's law of universal gravitation, it's called universal because you can use it to find the force of gravity or attractive force between any two masses. So not just or on Earth, you can go anywhere. You can just, as I said, calculate the force of gravity between my stylus and my calculator, right? So this here, ladies and gentlemen, you can only use this if you know the acceleration due to gravity. And for example, on Earth, and once again, near the surface, okay, so near the surface of Earth, we know G is on average 9.81, okay? However, ladies and gentlemen, if we don't have this value, you can use our universal equation, okay? All right. So, ladies and gentlemen, for example, because we can, let's calculate what the force of gravity would be between a mass and near the surface of Earth. Okay? So what I'm going to do is scroll down a bit so I've got some more space here. Okay. Now, ladies and gentlemen, I want to show you a couple other values on your data sheet. What we have here is you're going to see we have the radius of Earth and you have the mass of Earth. So anytime I give you a question and says Earth, well, I've already given you the radius, or at least part of the radius, and I will have given you the one of your masses that you need to use. Okay, so those values are right there. Don't forget that they're going to be valuable to you. Okay, so ladies and gentlemen, what we're going to do is I am going to write down some numbers here. So we're going to have the mass of Earth, okay, and which, according to your data sheet, 5.97 times 10 to the power 24 kilograms. And I'm going to have the radius of Earth. So from the center of Earth to the surface of your Earth, once again, data sheet. So 6.37 times 10 to the power of 6 meters. And I'm just going to use m of the object, whatever object, it doesn't matter. I'm going to leave it as m, okay? And we are going to calculate the force of gravity on m at the surface of the Earth. So, ladies and gentlemen, Fg, m1, m2 over r squared multiplied by big G. Don't forget big G. So Fg, now G, data sheet, 6.67 times 10 to the power of negative 11. M1, I'll make mass of Earth. Doesn't really matter which mass you make it, but 5.97 times 10 to the power of 24 times m, so the mass of whatever object. I'm just going to leave that as m. I'm going to divide this by our radius, 6.67 times 10 to the power of 6 squared. Ladies and gentlemen, this is the most common mistake that I see with this equation, is people forgetting to square the radius. Please, please, please don't forget to square the radius. If I'm going to make a mistake when making an answer key, it's going to be forget to square radius in my calculator. Rarely do I forget to square it on paper, but in my calculator, it happens. So please don't make my favorite mistake with this equation. Square your radius. So ladies and gentlemen, plonk this in your calculator. And guess what? We get 9.81344 meters. Well, ladies and gentlemen, times m. So let's rewrite this. 9.81 times m newtons. Looks pretty familiar, hey? Absolutely it does. So 9.81 is your G, and m is the mass. Well, Fg equals mg. So, ladies and gentlemen, that is one of the ways you can get G. Neat, hey? I love that. Okay? So, very, very similar if we just have written it as GM instead of MG. Nice, eh? Love it. Okay. So, ladies and gentlemen, let's do some graphing. I know this is a super long video, guys. Bear with me. This actually wouldn't be a bad point. Pause it, go get some tea, and then come back. Tea is good. You can never go wrong with tea. All right. Now that you have your tea, we're going to be sketching the shapes of the following graphs. And you, ladies and gentlemen, this is an important skill for Physics 30. And in Physics 30, guess what we're doing? We're going to be taking our graphs and we're going to be solving equations using y equals mx plus b. Okay, so it's something we're going to be doing a lot of next year. So this is an important piece to look at. Okay, so ladies and gentlemen, once again, what we do is we write our equation. And then we are going to set it up so this guy, so we're isolated for our y. Okay, so as remember the y equals mx plus b when you're graphing, and we want y by himself. Okay, so ladies and gentlemen, m is on our x. So I'm going to take everything else and I'm going to make it 1. Pick one mass, doesn't matter which one. Take everything else, make it 1, and add a proportionate sign. So Fg is proportionate to the mass. So when we look at this, Fg is directly proportionate for the mass. So as one increases, the other increases. Okay, so this is similar, to that graph pattern we were talking about earlier, where y equals x. Okay, so you are going to draw a straight line like that. Cool? Cool. Now for our radius, ladies and gentlemen. Same idea. Take your equation, make everything else 1. We want Fg to be on his own because he's on the y-axis. And then we're going to put a proportionate sign, make everything else 1. Now we're proportionate to 1 over r squared. That's important. Our radius is squared. So the farther away you get from your mass, your Fg is going to plummet. All right? So ladies and gentlemen, remember that this is similar to your, where y is equal to 1 over x squared. Okay, now this is what is called inversely proportionate. So the Fg is inversely proportionate to the square of the radius. Okay, that's not how to word it mathematically. So we would graph it like that. So the farther and farther away you get from the center of that mass, our Fg is just gonna tank. Sounds good? Alrighty-o. So, ladies and gentlemen, ready for some math? All right. Now this one, your favorite, that I like to call math wizardry. Insert groan here. It's where you guys generally groan. Okay. So, attractive forces between two masses is that many newtons. Okay, so that means it's Fg. Okay, if the distance between the two masses is W'd, okay, ladies and gentlemen, we're modifying this. So the distance is doubled. So that's going to be your radius. Okay, so our radius prime is going to be double what our original radius was, and one of the masses is doubled. Okay, make it M2, why not? So M2 prime is going to be 2M2. Okay, what is the new force between the masses? Okay. Now remember, ladies and gentlemen, that FG is also to G M1 M2 over R squared. So remember, ladies and gentlemen, same idea as what we've done before when we've done this particular style of question. So let's do some math with our modified. Same idea. We're going to be plonking in our values, our new values. We're then going to factor out those numbers, and then we will take this number and replace it with that. Okay. So what I want, I'm trying to find, I want to find FG prime. Okay. And my equation is FG is equal to G M1 times M2 divided by R squared. So now I'm going to plonk in my modified values. G stays the same. I chose to make M1 stay the same, but my 2M is double what it was. Okay, so I replace that M2 with 2M. I'll call it M2. And then we are doubling our radius. So I'm going to replace that R with 2R squared. Okay. Well, I need to do a bit of solving here. I need to square this. Now remember, when I have a square on the outside of the brackets, I have to square this and this. So I am left with G M1 2M2 divided by 4R squared. Okay, so as I'm squaring both of these, I'm squaring the 2 and I'm squaring the R. Well, I'm now going to factor out the 2 and the 4. So I'm left with G M1 M2 divided by R squared times 2 over 4. Well, that's a half. Remember that this is equal to FG. So this is equal to FG. FG equals this. So I am going to take this FG numerical value and replace this with that number. I'm going to write up here so I don't have to write on my face. So FG, the original, so 3.37 times 10 to the negative 6, and I'm going to multiply that by 2 over 4, or multiply it by a half, or divide by 2. I don't care. All the same, mathematically. Plonk that into your calculator, ladies and gentlemen, and with your sig digs, there you are. Fun stuff, eh? All good. Okay, ladies and gentlemen, next piece. Okay, ladies and gentlemen, calculate the magnitude, so I only want magnitude, I don't want direction, of the weight. Now remember, ladies and gentlemen, weight means FG of a 6.5 times 10 to the 2 kilogram spacecraft. So we've got our mass. Oops. That got written down weird. Let's try that again, shall we? There we go. That is this many meters above the surface of the Earth. Now, remember I told you we'd be doing a calculation about this. Watch this one. Pay attention. I'm fairly certain I did something like this on your assignment. Okay, I'd be shocked if I didn't, actually. Okay. Make so many assignments, I can't even keep track of exactly what's on them anymore. Okay, so let's do some math. Okay. All before setup. This is important setup. The R that we are going to use is going to be the radius of the Earth plus how far above the surface of the Earth that object is, the spacecraft is. So here's the Earth, there's the center, here's the spacecraft. We'll make it a TIE fighter because Star Wars. And so if our spacecraft's a TIE fighter, there's the radius of the Earth. There is how far the TIE fighter is above the surface of the Earth. And you need to add this plus this. So this number gets added to the radius of Earth. Okay? You're going to take your data sheet and you're going to get the radius of Earth off the back of your data sheet. Okay? Which is equal to, I'm even going to write this out. So the radius to the surface of the Earth plus, okay, from this guy from the surface up, plus the radius of Earth, add the two together to get your R. Okay, so you're going to take this value, you're going to add that to the radius of Earth from your data sheet. Okay, which is going to give you a radius of 1.052 times 10 to the power of 7 meters. That is the number that you are going to use in your equation. Please watch for that. Make sure you add those numbers together. This is one of that, besides squaring the radius, forgetting to square the radius. That's the most common mistake I see. This and then forgetting to square. So I've seen where just this is used. I've seen where just this is used. Don't do that. Okay, read the question carefully. Look for that phrase above the surface of the Earth. Cool beans? Cool beans. Okay, now M2, mass of Earth, right off the back of your data sheet. Okay. Okay, so ladies and gentlemen, let's begin. Write out your equation. I'm going to make a mistake. That's good, right? Wrong. You can't use this. Why can we not use this equation? We don't know G. We are not near the surface of the Earth. Okay, you can only use this equation near the surface of the Earth. Okay, we have to use Newton's universal law of gravitation. Okay, so I'm going to plonk my numbers in. Big G from the back of your data sheet. Oops, 11. M1, our mass of the spaceship, mass of our lovely TIE fighter. If it was the Death Star, then we'd actually have a more significant mass to it. I couldn't make it the Death Star. Death Star weighs way more than 650 kilograms. Okay, times that by our mass of Earth. Divide that by our radius. Don't forget to square it. So ladies and gentlemen, every single number you're dealing with in this equation is going to be in scientific notation for the most part. So this is where your brackets are going to become really important, and where I personally like to use, or the second E function. Personally, I like the second E, okay? Because it is so much neater than times 10 to the power of, than doing times 10 to the power of 4 times in this equation. Whereas second E, a lot faster. And it's also specifically telling your calculator that you want a number in scientific notation. Okay? All right. So, ladies and gentlemen, put these numbers in. You're going to wind up with a attractive force of between the two of 2,338.74053 newtons. Well, sig digs, 3 sig digs, 3 sig digs. When you look at the value of big G and massive Earth, that's 3 sig digs. Radius of Earth is 3 sig digs. So I'm going to put this to 3 sig digs. Now, problem, we got 4 here, so scientific notation. Okay, so this is going to round that guy up. 1, 2, 3. Okay, now in the question, I said magnitude of the weight, so I don't need direction. Cool beans? Cool beans. Alrighty, ladies and gentlemen, that is that equation. What we've got here, once I get to, there we go. These are some practice problems for you guys to have a go at. Do a couple of those, make sure you're comfortable with them. And then, ladies and gentlemen, pause the video here. Oh, and then we got some more practice problems. Here are some more that you guys can do. All right. So now is a really good time. Pause the video, take a break, go get some tea, do some of these practice problems, and you even like write down the time of the video. What is the time? Oh, I don't know. I can't even find it on here. So write down the time of the video, and then you can get some tea, do some practice problems, come back and do the next piece. Okay? All right. So before we start this next piece, I'm going to take my own advice. I'm going to go get some tea, and then I will be back. All right? So I'm just going to pause the recording if I can actually get the feature to pause. Okay. I will be back with tea. Welcome back, ladies and gentlemen. All right. Hope you guys have tea. I've got tea. Peppermint, very good for you. Yeah, very tasty. So, ladies and gentlemen, let's look at our next problem. Now, the next 2 problems are very, very important. I definitely have given you guys, I'm pretty sure, at least 2 questions like this on your assignment. And another vital skill for next year, Physics 30. We absolutely do stuff like this, but with electric fields. So the skills you are going to be doing here are going to carry over to next year. So this is very valuable. Star this, exclamation point this, sticky tab this, what have you. Okay. So, ladies and gentlemen, let's begin. All right. So 3 objects, A, B, and C, are placed that many meters apart from each other in a straight line. So here's our diagram. Love diagrams. Okay. If A and B have equal masses of 10 kilograms, and C has a mass of 15 kilograms, okay, write your masses under it. So much easier. What is the net gravitational force on B due to A and C? So what this is saying is, what gravitational force is this object B experiencing? Okay, so now let's think for a minute here. Object A is going to be pulling on object B. Gravitational forces are always, always attractive. So that means A is going to pull on B. Okay. So force A is going to be going in that direction. Okay. You could even call it like force AB if you like. I actually like that. FAB, so the force between A and B. The force of A on B. Okay, I like that. So now we can come over here and look at the force of C on B. Now remember, C is also pulling on object B. It's going to be going this way. Okay, we can call this one FBC. Why not? The force between B and C? Or the force of C on B? Whatever makes you happy. Okay, so ladies and gentlemen, we need to calculate the force here. We need to calculate the force here. And then we're going to need to make an F net equation to determine the net force. Okay? Okay. So, ladies and gentlemen, our force AB is going to equal GMA, GMB divided by R squared. Okay. Now, for sake of space, I'm just going to kind of write these in a bit of a line here. Okay. So 6.67 times 10 to the power of negative 11, which you can find on your data sheet. You do not need to memorize that number. Multiply that by mass 1, which is 10. Mass 2 is also 10. Divide that by our radius. Square your radius. Once you plunk that into your calculator correctly, you're going to get 2.668 times 10 to the negative 8 newtons. Now, ladies and gentlemen, keep all of these numbers in your calculator, okay? Don't delete them just yet. So we have one of our forces. Now we're going to need to calculate this next force. So FCB or BC, whatever you want to call it. Same equation. Okay, I'm going to plonk my numbers in. Okay. This is mass of 10. This is mass of 15. Okay, so watch for that. Radius is the same. Don't forget to square your radius. Don't make my favorite mistake. Okay. So, ladies and gentlemen, let's think for a moment here. Does it make sense that our numbers are so small? Yes, it does. Why does it make sense that our numbers are so small? Because the masses are small. The masses are only 10 and 15 kilograms. Like, do you have 10 and 15 kilogram objects flinging across the room towards each other? No, you don't. So when you're dealing with normal-sized objects that aren't planets and stars, you are going to have FG values that are tiny, and that's okay. All right? Okay. So now I need to think for a minute. I need to think about my F net. Well, my F net is going to equal, well, let's pick a direction. Let's make to the right positive, because why not? So it's going to equal F BC if right is positive. Now look, AB is going opposite direction of BC. So it's going to equal to plus my negative FAB. Okay. Okay. Now, ladies and gentlemen, this is important. You have to make sure you make one of them negative. These are going in opposite directions. I chose to make FBC my positive number because FBC or FCB is a larger force. And therefore, I'm going to wind up with a positive F net. Whereas if I wind up with a negative F net, I will have like a negative right or something like that. And that's just weird. Okay, or a negative left, which is really right. Yeah, so no, we're just going to go make the bigger force your positive number, and then you'll wind it with a proper direction. Sounds good? Okay. So I'm going to put my numbers in. Okay. So my FBC is my 10 to the negative 8. And I'm going to subtract my 2.668 times 10 to the negative 8. And then I am going to scroll down so I can actually write this nicely here. So I'm going to wind up with a lovely value with sig digs and units. Now I said net force, ladies and gentlemen. I want direction. Okay. So ladies and gentlemen, the trickiest part about this type of question is making sure you get the direction correct. Recognizing that because the gravitational forces are attractive, that object C and object A are going to be pulling on object B. Okay. So, and making sure that you set up your F-net equation in such a way that you will easily get your positive direction. And then you can just say to the right. Okay? All right. If you have any questions with that, make sure sign up on Google Meet. We'll go from there. Okay. Next question, ladies and gentlemen. And look, we've got objects in triangular pattern. This is where you guys are grown. Okay. So, ladies and gentlemen, this is another thing that is also super important. I give questions like this all the time in Physics 30, except with electrical for charges instead of masses for gravity. So, also important, the skills you get from this are going to translate to next year. Okay. All right, so ladies and gentlemen, we've got 3 objects are arranged in a triangular pattern as shown in the diagram. Object A has a mass of 25 kilograms. Object B has a mass of 20 kilograms. And object C has a mass of 37 kilograms. Okay. Calculate the net gravitational force on object B due to objects C and A. So we're going to be focusing on this guy. Now, we also need to be remembering that our gravitational force is attractive. Okay? So, object A is going to be pulling on object B. If that was a straight line, that would actually be a lot nicer. So I'm going to call this one, why not, FAB, so the force of A on B. C is going to be pulling on object B. Oops. So the force of C on B. Okay. So are you guys seeing what we're going to have to do here with our net, our first net? Hope so. I hope you guys are predicting that you are going to wind up needing Pythagoras, because if you did predict that, you're correct. Okay. So we're going to start out with the exact same method that we did last time. Okay. We are going to make or use our universal gravitation equation, and we are going to calculate our force of AB and CB. Okay, the gravitational force there. So FAB, G, M1, M2 over R squared. Now, what do I need to do with these guys? Throw them in as they are? No, convert to meters. All right. So, ladies and gentlemen, I am going to big G from my data sheet, 6.67 times 10 to the power of negative 11. And then we're going to multiply that by our mass of object A, which is our 25 kilograms. We're going to multiply that by the mass of object B, which is 20 kilograms. We are going to divide that by our 0.12, square the radius. Once this is put into your calculator correctly, you are going to wind up with 2.31597 ... times 10 to the power of -6 newtons. Once again, small number is okay because our masses are small, okay? So our forces of gravity here are going to be rather small. They're going to be negligible in reality, okay? So FCB, same equation. Plunk your numbers in. Okay, our mass of object B, 20 kilograms. C, 37. Radius, 0.17, square that. And you are going to get the lovely value okay. So we now have our two forces. So far, exactly the same as the previous question. However, our next problem is going to come in that we can't just simply add these now. You cannot simply add these. Okay, we've got one that's going up and we've got one that's going right. We need to draw our vectors tip to tail. Okay, if I see this, I am going to feel sad inside. I'm going to cry inside. Don't do this. Align your vectors tip to tail. Okay. So the same way that we did with any FNet scenario and on the 2D like we did in the dynamics unit. Okay. This dotted line is our FNet. Okay. So this guy here is your 1.7 times 10 to the -6. Okay. This guy here is your 2.3 times 10 to the -6 newtons. Okay. So guess what? Your FNet's this guy. You're going to do Pythagoras. Okay. So your FNets are a squared plus b squared square root. Already rearranged there. So you're going to take all numbers in your calculator. So our 2.31597 ... times 10 to the -6. Square that. Plus 1.70788 ... all the numbers in your calculator. Square that. Square root that. And you're going to wind up with our FNet, which is our C value here, as our 2.8776 ... times 10 to the -6 newtons. Now that's the magnitude. I said net force. Is force a vector? Yes, it is. Force is a vector. So, ladies and gentlemen, I am going to find theta. Okay. So, I am going to use tangent. Why am I not going to use cosine or sine? Less error. Okay. So because my tangent involves this guy and this guy, well, these values have the least amount of math done on them. If I'm going to use my hypotenuse, there's an extra set of an extra set of calculations done on that value C. So therefore, ladies and gentlemen, I highly recommend that you guys use tangent to reduce the amount of error. Okay. So, and I know it may seem minor that, yeah, okay, you're going to get the same number in the end. We're talking about one extra step. Let's go back to, I don't know, our book, The Martian, and any space travel. The number of calculations that you're going to be doing is going to be a ton. And you're going to have And every time you do a calculation, and even when your calculator is going to be doing the rounding, and NASA scientists use fancier stuff than this, you're going to wind up with some errors. You have to round somewhere. And that will build and build and build and build and build and build and build until you wind up with an error that you're going to, that your trajectory is so off, you're going to miss the planet altogether. Okay. So, ladies and gentlemen, in this case, it's not a crisis. But for those of you who are just thinking about going into a physics-based career like engineering or something, then it will become more important. Okay. So I'm going to use tangent. Okay. So my tan -1 is going to be my opposite over my adjacent. So there's theta. I'm going to use my opposite. I'm going to divide that by my 1.7 times 10 to the -6. And I get theta of 36.407 degrees. All right, so I'm going to scroll down so I actually have some space here to write down my answer with sig digs in units and direction. There's a lot involved with this. This is like at least a 4 to 5 mark question. Probably 4 to 5. I can't remember what I put this one as on your assignment. There is one of these on your assignment. So your F net, ladies and gentlemen, once you've rounded it, 2.88 times 10 to the power of -6 newtons. Our angle with sig digs, 36.4 degrees. Now I need a reference. Okay, there's is north, that's going east. Okay, so this guy is going to be east of north. So the theta is that this line here, our F net, is east of the north line. Okay. There's your answer. Okay. Ladies and gentlemen, what I would recommend here before we move on to Cavendish is pause the video, drink some of the tea that you've made, and then come back to this, maybe do a couple practice problems. We're not going to spend a ton of time talking about Cavendish. But this is more theory. Okay, so pause the video, drink some of your tea, and then come back. We're back. Okay, so now that you've had some tea, I haven't had my tea yet. I'll have tea later. Okay, the Cavendish experiment is how we got the value for big G. As that's a question you guys may have had earlier. So where does this number come from? How do we know what one piece of gravity is? Okay, so Cavendish was a scientist who came up with this number using a device called a torsion balance. Okay, so he hung a bar from a very flexible wire, and so that way this bar that had two masses on the end and was balanced, and it would hang perfectly still. But it could rotate freely. Okay, so once it was hanging perfectly still, he put masses here. Okay, now these masses, he knew the exact weight of, or the exact mass of, excuse me. So he got their mass, he calculated their mass, and he knew the masses here, he calculated their mass, and he knew how far apart they were. Okay, he knew the radius. So the only thing he didn't know was big G. And ladies and gentlemen, he was then able to, I can't scroll down because it's still on the pen feature. There we go. Okay. So with these equal masses fixed to the other end, these larger masses placed there. And once again, they were placed pretty close. They had to be placed close to each other. Why? Too large of a radius, the FG is going to be too small. Okay, so once the torsion balance was to move freely, these smaller masses would be attracted to the large fixed masses because of gravity. He was then able to determine the value of big G by how much the torsion balance rotated. So the angle of rotation. That angle of rotation is what allowed him to calculate big G. You do not need to repeat the experiment. You do not need to worry about his calculations. But I'm fairly certain I took off the Cavendish question off of your assignment, and you won't get one on your test because you're not writing tests. But any questions I would give would be like what variables were which. So for this one, he was able to manipulate different variables in separate trials. Now, if he manipulated the distance at what the places, the distance would be identified, controlled, and responding. Well, remember your controlled variables. If your controlled variables are the things that you keep constant, well, he kept the masses the same. Okay. And if he manipulated the distance, well, that's your manipulated variable, what he's changing. The responding variable, now remember, your responding variable is the variable that changes as a result of the others. So our responding variable would be, well, the force of gravity between the two, but more directly, more accurately, it would be the amount of rotation. Okay. All right. So, ladies and gentlemen, that is the end of this video. I've got some practice problems here in your workbook. Give some of those a try. And thank you for hanging in for such a long video. I know this one's a bit of a beast. You guys are awesome, rock stars. So ladies and gentlemen, this is a very important video. The topics in here are going to be coming back next year in Physics 30. So we spent so much time with this topic today. All right, I hope you guys have a good rest of your day and no fires, injuries, or explosions. Wear sunscreen. It's starting to get sunny out. Okay, where's my stop button? There's the stop. Have a good day, guys. Bye.